So if you have any question, you can ask me anytime in between the slides. Okay. Just a moment. Let me set up a few things here. Yes. So today we are going to learn about, we already discussed about lenses, how the lenses are constructed in electron microscope, how they are different than the visible light microscopes. And today we are going to learn about last two topics, apertures and resolution. So we are going to learn the physics of apertures, and how the apertures are made, what is their significance in electron microscopy. We are going to also learn about astigmatism. So today we are going to learn about, we already discussed about lens. So I'll browse through the slides which we already, just to cover a few things. Just a moment. Yeah. So then we discussed about differences between visible light microscope and TEM, uses of aperture, that we can control the beam, select between imaging mode and diffraction pattern mode. After that, we discussed about a comparison between light optics and electron optics. And if you remember, we also discussed how to set the conditions of condenser lenses, objective lenses, to get different kind of illumination. We discussed about different planes, like object plane, image plane, and also plane of the lens. We discussed about back focal plane, front focal plane, lens equations we discussed. We also discussed about magnification, demagnification, and it is a relation with the angle of collection of the beam, right? Alpha and beta. So we discussed about how when you enlarge alpha and reduce beta, how you can increase the magnification. Decreasing the alpha will decrease the magnification here. Similarly, you can change the magnification by varying di and do. Do is basically towards the objective plane, and I is for towards the image plane. So that's what we knew. After that, we discussed about difference between over focusing and under focusing and focusing, and we also learned why under focusing is so important, or out of focus is so important, whether it is over focus or under focus. In TEM usually we are under focused. Right? Today we'll discuss what is the reason for the reason. Basically, it is to control the aberration. And initially, the design was quite imperfect. We discussed of lenses. Okay, so lens design, little bit we discussed. Also the hole pieces. Also we discussed about future of superconducting lenses, how the superconducting lenses are going to change the way we do electron microscopy. After that, we had some discussion on why electrons take helical path, not the straight path, the way we show normally in the sketches. So the electrons take helical path as because of the reason is that these electrons are basically at certain angle with respect to the magnetic field. So this Lorentz force, the two components, basically decides how the electrons take this cyclotron behavior with the radius r is equal to mv divided by ev. So this is all described here, the parallel component and the perpendicular component. And parallel component basically give it the forward push, and the perpendicular component, perpendicular to the magnetic field, basically induces the circular motion because of the outward, radially outward uh, push. So today we are going to discuss about apertures and diaphragms. So diaphragm, basically we use this term apertures for this kind of opening, and but this opening is basically this hole in the disc. There is a metal disc, and this hole which allows the electrons to go through, that is called as aperture, and the disc itself, which is a metallic disc, is called as diaphragm. So in day-to-day language, we basically use aperture for diaphragm as well as for aperture both. But please note that this is the metallic object or metallic disc with a hole between of various diameters are that is called diaphragm, and then hole itself which allows the electrons to come from specimen or from the electron source, that is called aperture actually. Okay, so this is basically called limiting aperture. Limiting means you can see that the size of the aperture decides at what angle. So basically the size of aperture decides the maximum aperture, the collection angle. So your beta is also decided by this distance, obviously, this distance between aperture and specimen, which is normally fixed. But if it is a lens, not the specimen, suppose it's not a specimen, but it is a lens. So if you change the strength of this lens, then you can change this basically how this beam converge or diverge. So you can control how many electrons will be allowed through this limiting aperture. So you can see that these rays, dotted rays, are excluded. They don't reach here. So unwanted electrons are stopped by this diaphragm. So essentially the material has to be metallic because you do not want accumulation of electrons, right? So normally this material is of refractory metals, mostly molybdenum and platinum, I think. So it should not get contaminated so easily. So these are the properties. Why do we need refractory uh, metals? Because so this tends to get heated because the constant bombardment of electrons. So electrons lose, because it's thick sheet, so electrons lose almost all the energy to these diaphragms. So these diaphragms undergo a lot of beating actually, from a lot of damage over the period of time from the electron beam. You can understand that a lot of knock-on damages and also heating. We discussed about three kinds of beam damages. So out of that, one was radiolysis, second was knock-on damage where atom itself can be knocked out, third one was heating. So last two gets very serious here. So heating can be avoided because it is metallic. But still there will be some heating. Fine. Another very important part here, which is very highly practical, you people may not realize, but for a person who is operating the TM for several months and several years, what happens? All these volatile stuff from your sample. Suppose sample is not dried properly. Uh, so what happens that when you put the sample in the sample chamber, so the contaminants from, suppose sample faults and all kinds of things, so these contaminants can start depositing uh, at the edges of this aperture, right? So, so and over a period of time, because there is a lot of heat generated, so these those uh, debris or those impurities will form a coating, thick coating. And now just imagine that then then there will be, suppose there is a non-conducting coating or over one part of this aperture, so there will be some over a period of time, even if there is a small accumulation of electron locally, local accumulation is there. So just imagine that any incoming electron, this also starts acting like a lens, because there will be Coulombian repulsion from that part, and you start getting beam distortions, all kinds of. So that is the reason you get astigmatism. That beam doesn't remain spherical in nature. So astigmatism, one of the reasons behind astigmatism and all those problems is because of problem with the aperture. So periodical cleaning of apertures are required. There are so many apertures, they all needs to get, this is just one example, there are so many apertures in the electron beam path. So why, because you now you can understand the severity of these things. Some many times what happens that chemistry students especially, or many other students, they do not understand what it takes to run a machine. So they, sometimes students don't feel the science behind that. They think that it is just some routine machine, and why it is not working for so many months. So now at least you get a flavor that how complex small things can be. So replacing this is not that easy. You have to open the machine and you have to clean it up, and then you have to vacuum entire thing and align the electron beam perfectly, parallel to the optic axis, and it should reach where it has to reach. So this is not a joke. So every part of the electron microscope, there are so many lenses and aperture. So beam should you can just understand that there is a small deflection from the top at a small angle, a very small angle. So in the image plane down there, your beam can deflect at a very large angle. So it's a serious thing. So that's why these things, small things, becomes very serious when you try to image your sample. So this angle has got a lot of implications on the resolution, not just on the how many electrons you collect. What quality of electrons is decided by the aperture. Okay, so apertures decides the quality of electrons. For example, you can select what kind of electrons you need. It decides the beta. Beta is actually decided by aperture also, not just the lenses. Second thing, your astigmatism, quality of the diaphragm also decides the astigmatism. So I have listed here actually from various topics that aberration limited resolution of the image formed by the lens. Spherical aberration and chromatic aberration is strongly affected by the collection angle. When I say strongly, you can understand the beta is, to the power 3. So any small change, small increase in the beta, if you increase the collection angle, so this spherical aberration is going to increase. The CS is basically spherical aberration coefficient, which is basically for objective lens. Okay, primarily because there are so many lenses that natural question comes that which CS is serious, which CS is the CS which manufacturers code. Suppose you buy TEM, The natural question is that which spherical aberration is quoted, which one is serious. So please note that it is an objective lens spherical aberration. So spherical aberration is which limits the resolution is proportional to beta, not inversely proportional. On the other hand, second point, if you see diffraction limited resolution, Rayleigh criterion depends upon the collection angle inverse, where that collection to the collection inversely proportional to the collection angle beta. Okay, and depth of field, depth of focus also get affected. So if you have larger aberration, so you have, in fact, so as we noted that we'll see it later on, but smaller aperture gives larger depth of field. And I've given in my class many times these examples. You can take example of your mobile phone, or you can take example of your DSLR, right? Image contrast get affected. Collection angle of the electron energy loss spectrometer, will come to that. Angular resolution of DP, astigmatism, okay, right? Bad aperture can cause this. So astigmatism is again proportional to beta, and the defocus, delta F is basically defocus. And defocus, as I mentioned in the last lecture, is fundamentally important in transmission electron microscopy. Delta F is non-zero. Please note that. In optical microscope, delta F is usually 0, but here it is non-zero. And why it is non-zero? One of the reasons is basically you take care of the aberrations actually. So it basically it acts like a counter dose to the aberration. So aperture can also perform some other functions, such as protecting the specimen from stray radiation in the illumination chamber. So again, you can see this is an objective lens, this is your sample. So these are your objective aperture. So the different sizes. So usually this is a metal plate. So with various holes of various dimensions. And this is, as I mentioned, that it is either platinum or molybdenum, which are both refractory metals. What do we mean by refractory metals? That melting point is higher than other metals. So you can see that you can select different sizes of apertures here. So the electron beam passes from there. So you can see that now outgoing electron beam is the angle is different than this electron beam, and thinner. So basically, it gets thinner below the aperture, and after that, it interacts with the objective lens. Objective lens is immediately above the specimen. So this is lower objective lens, and down there is a upper objective lens and lower objective lens. So you can control the aberration in condenser lenses. Okay, above that there are condenser lenses C1, C2. You know that, but so it can be corrected with the lens settings again, right? But finally, the beam which enters into the sample, the final quality of the electron beam and aberration and all kinds of things decided primarily by this final lens. After that, these electrons enters into the sample, and once the electrons transmit from the sample, and below that you have the lower objective lens. Again, the quality of that lens also affects the quality of imaging. So any error in these lenses, objective lens, affects the resolution, because this is next to your sample, and further it just get magnified by M. So when you try to magnify the image in the image plane, the aberration also get magnified by, suppose you are magnifying by 1000x. So aberration also get magnified by 1000x, because you are magnifying the whole entire thing. So that's the reason that you have to be very careful here itself. After that, it just get magnified. Everything get magnified. when you send the beam down to the projector lens 1, projector lens 2, and finally to the screen. So role of aperture is highly important in the beam quality, as important as the quality of the electron source, electron lenses, and aperture. These are three very important parts. So that's why I'm putting a lot of time here um, on apertures, and you will start noticing that how important these roles are. So this is real life pictures of different kinds of apertures. So this is aperture folder. So you can replace this. You can unscrew this thing from here, and then you can replace this plate on the holder, and you can choose from which of these. This is a entire strip or diaphragm, you can call it, right? And you can insert from here, okay, and you can basically pull it out or pull it in to select which one you want. So, so it has to be shape has to be highly spherical, because you do not want non-spherical. As I mentioned, that non-spherical shape uh, can be due to contamination depositing one side of the circumference, right? Just imagine your coffee mug or tea mug when you take tea in the morning, and there is some malai over that, right? So you take the malai out sometimes and deposit it on the circumference of your tea mug, right? And that get deposited. So in apertures in electron microscope, you can't do that. So your malai is actually like malai of your sample, actually, okay, it get coated there. So when the electron beam comes from the electron source, so that malai acts like an extension of your aperture, right? It becomes an aperture because electron beam doesn't know that it is not an aperture. So so then it leads to distortion. It leads to astigmatism primarily. Okay, so we'll discuss about that. So smallest diameter, it's a mechanical limit. Usually it is 10 micron, and it can be as high as big as 300 micron. And usually that strip thickness is usually again in tenths of micron. It can be thicker. Thicker is better, but again the price goes up, and you have to replace it because it get permanently damaged. Uh, right. Uh, so thicker aperture can prevent X-rays actually from, because X-rays are also formed, so that can block the X-rays. Okay, thicker ones. So you can see there are different numbers given to the aperture. These are the numbers, and these are corresponding aperture dimensions. Number 4, number 3, number 2. Usually they identify with the numbers. So different kinds of apertures have different uses. So number 0, which is the largest, is used for alignment of the electron chamber, electron beam, and the next smaller one is used to observe observation of high probe current, actually shallow, because it will give you shallow depth of field, as I mentioned, right? Because larger the aperture, shallow the depth of field, smaller the aperture, angle, the smaller the angle, you have a much deeper depth of field or depth of focus, both. The depth of field is in object plane, and depth of focus is in the image plane. Okay? Both are important concepts. So then further you can go to 30. So this is for ultra high resolution. The probe current goes low, obviously, because you're cutting most of the, if you take this smaller aperture, so you're cutting down almost all the beam. You have very thin beam, but then you have very large depth of field. So that gives you clarity about, suppose your sample is not uniform, there are ups and downs, so you get better quality of images. The next slide is, as I mentioned, contamination of aperture can cause astigmatism. Astigmatism, again, these ideas, these terminologies are all from visible light optics. Okay, optics is obviously visible light, but now optics is loosely used term in other sciences also. For example, we call electron optics. Okay, optics is usually reserved for X-ray optics, also we call it. Optics, the term itself came from visible spectrum only, but now we loosely use it. So when I use this term, so please do not get confused. The clarity should be there. So contamination can affect the homogeneity of the electron beam, as I was mentioning. So in our eyes also, we have astigmatism. Most of the time when the kids get glasses in young age, it is usually the astigmatism. It is usually astigmatism when the kids get, so you might notice that they get these cylindrical lenses to as a corrective lenses, right? So there are spherical lenses and cylindrical numbers are there. So you can see that this is a normal cornea and this is elongated. So it's exactly same thing happens in the electron beam. So electron beam should be like this. Okay, when it get elongated in certain direction, so that is basically, actually elongation can lead to the problem. So aberration is again very important part, and I avoid a lot of text, but I could not avoid this text because it's so interesting, so funny, so humorous. Actually, it's very nice. Actually, I mean, there are 2-3 slides which will excite you a lot if you get connected to that. So when the first person, the von Leeuwenhoek, first constructed the light microscope, basically it was a, he collected 2-3 lenses and then made a compound microscope, and right, you have to do the mechanical movement of the lenses up and down to magnify certain things. So at that time, the glass lenses were they were full of problems actually, uh, right? And then people started perfecting these lenses later on, the glass lenses, right? But when it comes to the electron lenses, magnetic lenses, Bush was the first person who successfully made the magnetic lenses, right, for the electrons. And Ruska used actually his lens technology to make the electron microscope, Ernest Ruska. Uh, After that, we have not progressed too much, and lenses are very imperfect. How imperfect they are, basically, those things can be compared. So we can compare the best electromagnetic lenses to the equivalent of using a bottom of soft drink bottle, Coca-Cola or something, as a magnifying glass. If I compare precisely, so the way you use that, it's so imprecise, so imperfect. So that is the quality. So even we are able to. That's the reason that we are not able to reach to the theoretical limit. There are other problems also. We'll discuss not just the lenses. There is a problem with the beam, also chromaticity of the beam, monochromaticity of the beam, which is far from perfect. Second thing is that another common description is that, just to give you an idea what kind of problems are there. Suppose you wear those electron lenses in your eyes. I mean, basically similar version in optical lenses. For example, I have these glasses. If I wear the same imperfect lenses which we are using in electron microscope, I'll be I'll not be able to see. I'll be blind actually. Even if I have normal eyes, I'll not be able to see. So that kind of imperfection is there. Uh, Last line is very important actually, that these imperfections, they limit resolution of the microscope fine, but it's a paradox that these imperfections also help us to get better depth of focus, as we have seen, and we will also see in coming slides. Our depth of focus and depth of field also becomes better. That's why electron microscopes are known to have far better. So this spherical aberration term was highlighted in media uh, uh, from this launch of first time. There was a lot of interest in spherical aberration when this Hubble telescope was launched for extraterrestrial exploration, because as all of you know, as science students, that light beam uh, starts flickering when it reaches to the earth because of the multiple refraction from in our environment. So if you have any telescope on earth, then a lot of stray noise enters into the uh, telescope light sources. That's why most of these telescopes which are on earth, they are mostly perched in the areas where there is no light deep in the forest or up on the hill. So stray light should not be able to reach, but still you cannot. Um, basically, any image from any image or any light beam coming from far away galaxy starts wobbling. It's wobbles actually. It moves in time. It starts wobbling. The image actually drifts all the time, and um, the light signal is also very feeble. So then scientists thought, okay, let us put it on a space shuttle, the entire telescope, and let us launch it into the space. And we can also, it will give us a handle that we can take this telescope and orient it on any star or galaxy we are interested in. So, the contribution of Hubble telescope, it has given immense information about the interstellar world, what we see today, about the cosmos. A lot of information about cosmos has come from this Hubble telescope. And there is an interesting story about Hubble telescope that when its lens was being cast, so the glass lens, it was probably a very huge lens, so 6 feet diameter or more than that. I don't remember. But then after the lens was cast, so then they realized that this lens has got spherical aberration. So, so it was not spherically similar off axis. So, so, so that was the problem. So then there was uh, uh, right. There was some corrections which were done. So spherical aberration essentially is that if you have this spherical lens, why do we call spherical lens? Basically, it's part of a sphere essentially. If you chop it off, you take a glass sphere, and then if you chop off one from one side, you get similar to what it is. The curvature of this lens, if you complete the sphere, then it's basically another point is, I'll come to that. So if you have this parallel beams coming uh, towards these lenses, so in we are, because considering electron lenses, right? So the magnetic field towards the edges, which is much stronger. So magnetic field is much stronger towards the edges here and here. So if it is stronger, so any electrons which are passing from the edges, they will focus at at a closer distance, actually closer to the lens. For example, this dot here, and all the rays which are passing through the middle of closer to the optic axis. This is optic axis, dotted line. They focus at a farthest point actually. Now, so this line. Uh, this is your horizontal okay, or longitudinal longitudinal aberration. So now, so these are basically a series of focal points. So where will you call as your image plane? Where will you put where will you put your screen? Where will you form the image? Which, this point or this point or this point? And so essentially what is happening, that a point from in your object plane is now a disk. So this is all spread out, which you do not want. Basically, you want this to be a point. But on the other hand, you have increased the depth of focus. This is depth of focus, right? Other side you have depth of field. So you can focus anywhere. That means in this large distance. Uh, so uh, so if you see that, if you see this ray diagram, uh, this circle around this beam is the smallest here, where these beams crossect actually somewhere here. So this is called the plane of least confusion. So this is where you measure the resolution. So where will you measure the resolution? Here, which is here, which is here. Actually, it is quite worse. You can see the disk is much larger here. So if you put your camera here to capture the image, so the point will become a large disk. So resolution is very bad here, here, and it becomes worse. You can see it is still broadening, but it is the narrowest somewhere here, right? So you would like to the radius of this circle around this is called the spherical aberration. It's counted in the spherical aberration, S in beta cube. So beta, if we look at the equation of beta, so there this R, this radius comes as a factor. Now you can have similarly you can have spread this kind of also. So you essentially you get this blurry image instead of sharp image. The larger the aberration, the blurrier the image will be. So it compromises your image quality. Fine. Next slide, we'll see. This is better pictured here, and again it is a very rich slide, so I'll spend a lot of time on this slide. So why it is called spherical aberration? So it's a natural question, because the effect of this aberration is to take a curved wavefront and increase its curvature actually. So you can see that if you see the solid line, if you see this dotted line, people who are viewing me on mobile phone, they may have a problem. So this dotted line is without the curvature. So this is the original curvature before lens, right? No aberration, and this is the collection angle beta. Let's start from this point P. The point P is basically some point in your specimen, and you want to translate the point to a point. This point should be a point here somewhere, right? This is one point. There are millions of this kind of arrays of points. You can call it pixel or point. So this point, when it goes through this lens system, aperture system, and lot of lenses, so finally it should be a point here. Why it is a disk? So if you notice that this spherical wavefront, when it passes through the imperfect lens, so on the other side, the radius of curvature of this spherical wavefront does not remain the same. It starts increasing. Okay, it starts increasing. If you just bend it more, you will see that you are shifting the focus closer to the lens. You can see the more you bend, you can see that this collection angle will become larger and larger. And so if you go into the reverse direction, if you decrease the, if you bend it opposite direction, then if you increase the radius of curvature, so finally it can happen other way around, this side also. So CS is, so that means CS is basically non-zero spherical aberration coefficient. So now you can see that, suppose this is your original Gaussian image plane. That means beam was supposed to be focused here. If there was no spherical aberration. But now in practical life, we have the spherical aberration, so we cannot consider this as a image plane. So now if we see that this is the lowest, the point of lowest radius, so that's why it is, this is D minimum, right? D minimum, D is basically your resolution, okay, right? So this is the minimum point where you can find better resolution. So, um, so you can consider this as the image plane instead of this. So, so this here the disk diameter is called as disk diameter is 0.5 cs beta cube. Uh, at this point in the image plane, the disk diameter will be 2 to the basically the spherical aberration is counted and in this plane, not in this plane. This plane is where you can operate. Okay, this is the minimum point. But actually, when you buy a microscope, you ask the resolution in this plane, so which is twice, because radius is cs beta cube, right? So diameter is basically 2 times cs beta cube. So now you can understand that when you buy, so you have to consider the values in this plane, right? So this is very important actually. Perhaps you are learning it in this depth for the first time, right, in your life. This is the first time, and these are quite complex topics. It's not easy to understand on its own. So now you can see that this is the transverse, and this is longitudinal spherical aberration, and this is This is basically what we call paraxial ray focus, and so you can meditate on these uh, graphs, the schematics. Um, Yourself when you get the slides later on. The spherical aberration in the objective lenses, basically in STM, condenser lens is also the culprit. So main culprit, as I mentioned, is objective lens. So, right, other lenses just magnify any error uh, the objective lens introduced. So if you correct, so if any correction has to be done, it has to be done in the objective lens, because after that some electrons exit from your sample. Um, so I'll move further. It is equally harmful in the condenser lens in an analytical electron microscope or STM, which we use. Suppose you are using condenser lens to condense the beam, okay, to this on the sample, converging the beam. So then it's equally harmful there. So you have to fix all those things. Um, so this is an expression to calculate the disk diameter. As I told you that now you have a disk actually. You are getting a disk rather than a point. This point becomes a disk. So the radius of this disk is taken as this is taken as CS. CS is a constant, and this constant is basically a constant for that particular lens. So when you buy the microscope, CS actually value comes with the lens. That okay. So you must write in your research articles in the materials method that this is the CS for the particular lens which you are using. So CS is generally equivalent to the focal length of that lens. So CS is generally in the millimeter. Please note that. I repeat this. You might have missed it. So CS is generally it is in the millimeter. Okay, why it is in the millimeter? Because that is the focal length of typical electron lenses. Actually, lenses in the when I say electron lenses, I mean that lenses which are used in the electron microscopy. The right term is basically magnetic lenses. These are magnetic lenses in nature, magnetic field. But I sometimes use electron lenses. Also in literature, we use the term electron lenses. But either way, it is fine, no problem. As long as you learn the basic, as long as you know the basics. So in high resolution instrument, for example, if you have high resolution TEM, so this CS value can be lower than 1 millimeter as well. So what you need is basically shorter focal length objective lens. Okay, this is for objective lens, which is kept very close to the sample. Few important point. So Yes, so as I mentioned that when we refer to the image plane, so this equation you have to multiply by m because you are magnifying, right? So suppose you are magnifying by 10,000 times, so you have to write this number by 10,000. So so this first you calculate this, you put the CS and you know the beta, right, collection angle, and then you multiply. So that becomes your this aberration, which is quite significant. Uh, it is determined by beta finally because it finally is determined by aperture because beta is by aperture. So real lens in a real lens the value of theta in equation which describes the angle of electrons in the optic is replaced by maximum angle of collection. Objective lens aperture actually finally that is the most important. Beta is decided by that. And so reducing beta gives larger reduction in data, right? So because it's power 3. So, this second line, this next line is very important. That we have learned so far that for optimal resolution, we need larger beta. Now we are saying that we have to reduce beta. So these are uh, uh, there is a contradiction here, right? These two lines are contradictory to each other, as we mentioned in the beginning of this lecture. That so the compromise is you. So we have to reach compromise somewhere between two lines. That one factor prefer reduction in the beta, and another factor uh, prefers uh, increase in the beta. So compromise is used somewhere. That beta should be around a milli radian, 10 to the power minus 3 radian angle. So that leads to resolution around one angstrom, which we see day to day life. We'll discuss about what do we mean by resolution because there are two kinds of resolution: point resolution and line resolution. So here we are talking about point resolution, definitely. So you can see in a laboratory which is not aberration corrected. Uh, there, just let me put the charger. So next point. So this is for EM. This is for you. Next point, that how EM vendor, electron microscopy vendors, they take advantage of plane of least confusion to confuse you. Okay, so it's very humorous line. So they take the plane of least confusion by quoting the plane of least confusion to increase your confusion. So this is the plane of least confusion, and they will quote that this is what D minimum is, and you get confused. So now you will not get confused. You want the resolution in Gaussian image plane, not in the plane of least confusion. So I repeat this. I repeated earlier also that resolution you must ask in the Gaussian image plane. So they can say that, oh, this is the resolution of the microscope. So there is a big difference when you calculate the resolution here or here. So this is the Gaussian image plane, right? Remember we discussed in the last lecture what do you mean by object plane and image plane. So that has to be really okay, factored on seriously. So now question is that how do we correct CS? You don't want to correct it because it's very expensive to do that. So it can be the cost, earliest cost is to be 35, 25 crore rupees for just one microscope. So this problem is quite old. It was investigated by a theoretical physicist Scherzer, German person, Otto Scherzer. I'll speak about him, and he gave this lens design that so basically there are corrector lenses also, so that those companies, they put the corrector lenses uh, in in basically addition to so these are highly complex computer controlled quadrupole or hexapole or octopole kind of things that makes the CS zero. So CS is non-zero. So when you add those characters, CS comes down to zero. So I'll tell you very interesting things in coming slides, that even if you work on aberration corrected uh, electron microscope, where essentially CS has been made zero. So if you make CS zero, that means this aberration is zero. So basically a point will become a point, right? Essentially. But you know that that means the resolution should be infinitely zero. So I mean, it's just it's never zero, but it is reaching towards zero basically. But do you get the resolution that small? No. Finally, it is limited by the Rayleigh criterion. Remember that you can't beat the Rayleigh criterion physics uh, on any condition. But there is one more thing which you have to consider seriously before you start worrying about the theoretical limit, which was given by Rayleigh. Uh, I'll come to that, and it is very interesting because that has to do with the sample. Your sample, actually, your sample also introduces the aberration, chromatic aberration, and that's why we always say that thumb rule is thinner the better, thinner the better. So that is the final point of today's talk. This is just to remember. Just if some people are curious, so these are some of the designs for just for curiosity. These are some of the design for CS characters. So you can see that there are different kinds of complex lenses kept close to each other. And finally, you can correct the spherical aberration. Yes, this is the final culprit. Even if you have several $1 million machine with spherical correct and highly monochromatic. So chromatic aberration can come from any deviation from monochromicity of the incoming beam. So thermionic emission in the electron sources, the chromatic aberration is larger. So there you have larger disk in the plane of least confusion. Okay, even if you fix it by using, to some extent, you can fix it by using field emission gun. So then your chromatic aberration becomes further smaller. If you want to make the chromatic aberration uh, close to zero, then people use monochromator in the electron source. After electron source, the electrons passes through a monochromator. So monochromator is nothing but basically a grating. Grating is nothing but crystal with particular D values, interplanar values. So basically, monochromator works with the Bragg diffraction. It just diffracts, it just disperses multiple lambdas, and you after that you can like prism. Prism can disperse white light. So similarly, here there is a grating, or you can call it a crystal with predetermined D values. So when this electron beam passes through that kind of a grating, so it gets dispersed like 7 colors in prism. And after that, you can select particular beam which you want and reject the other uh, lambdas. So that is the principle of monochromator. So these monochromators are highly expensive. Actually, it will make a deep cut in your pocket if you have to buy that. Okay. Uh, so, but that corrects that's the final thing. So chromatic aberration is again the term which is taken from geometrical optics. Okay, so if you just I mentioned that that first thing which you have to worry about chromatic aberration is basically your source. So cold fact, the basically the your chromatic aberration uh, can be because of the dispersion in the uh, energy spread in the electron source, which is around few hundred milli electron volt for cold field emission gun, and for thermionic it can be worse than 1 electron volt. Uh, yes. So next, you can see that if you have several, you have energy spread. So different kind of beams will focus at different points. So that also leads to varying range of focal points. Actually, it's not as bad as it is described in the figure. Um, Yeah, so as I mentioned that you can use monochromator, but this business is very expensive, so you can't afford it usually. Uh, if you look at now, we have to we want the same equation, similar equation as we got for spherical aberration, because that equation is very useful for us. We are not interested in these things. Finally, we want some number. So let's start from specimen. So this is specimen, and then this is the collection angle by this is the lower objective lens, and finally, as I mentioned that when the electron beam enters into the specimen, it can undergo a lot of lot of energy loss processes. We have already learned in the lecture where we discuss about inelastic processes. So all those inelastic scattering processes may induce some energy loss. Please note that, and that can here what we're learning that even if you have corrected, we are not considering the aberration from the source. Suppose source has been fixed, so how the sample can contribute to the chromatic aberration? So that's what we are considering here. So inelastic processes which are happening in the specimen can create electrons of different energies, right? For example, an electron transfers some energy to the core electron to produce X-rays. So the outgoing electron will be 300 keV minus, for example, few 1 or 2 keV. So that is energy spread. Suppose one electron of 300 keV underwent uh, energy loss in kicking out the secondary electron. So the outgoing electron will end up as a contributing to the chromatic aberration. So here, thicker the sample, more these kind of inelastic processes will happen if you take this sample thicker and thicker. So what will happen that electrons which have undergone energy loss will focus somewhere at this point, and the electrons which have not undergone energy loss will focus in the Gaussian image plane. Now, if you see that, if you see that this becomes your, because this beam is also spreading, it's not uh, extended here. So if it is extended, you will find that this is your somewhere here. This is your plane of least confusion. So your Gaussian image plane will be very broad because of these energy loss processes which are naturally happening because of type of your sample. So uh, yeah, so objective lenses bands lower energy that you can see from the equation, lens equation. You will notice it there. What is written here, that lower energy electrons are bent much more stronger, and they will end up at closer to the lenses. So this lower energy, the lower the energy, then these points will start focusing here rather than closer to the image plane. So finally, we have this radius of this spread. This spread is because of the chromatic aberration. So the disc formed. Remember, we want point to be imaged as point, but here because of this broadening, because of aberration, the point is being imaged again as a disc. So this is one more disc. The one more type of broadening, and this time because of chromatic aberration. So the radius of this disk is given as Cc times delta E, which is because of all the factors. Delta E can be because of your source. It can be because of your sample, as we have mentioned. Any dispersion, any deviation from E0 number. Suppose E0 is 300 keV. So any deviation from 300 will contribute to delta E. So larger the delta E, so larger will be this disk size. And if you please remember that next point is beta. So larger the collection angle, larger the aperture size, again R chromatic will be larger, which is in contradiction with the Rayleigh criterion, where beta comes in the denominator, right? Rayleigh criterion D is inversely proportional to sine beta. So you can see that here the aperture plays a big role. So CS like CS, CC like CS has a length, unit of length. Okay, so C, the R chromatic is quite a large number comparison to atomic diameter. That's atomic dimension. So that is the reason that many times you're not able to see the rows of atoms clearly because you have not taken care of chromatic aberration. So that is the reason that if you have the same lenses, for example, you have same very high quality lenses, and you take HRTM and with very high quality lenses, and you change the source from field emission gun. Suppose your field emission gun is not working, and you replace it with the easily available thermionic gun. The question is that will you still get those diffraction? Those lattice fringes? No, but everything else is same. Your lenses are the same. Your sample is for the same sample and same condition. Uh, your CS is same because lenses are same. No, because you may not be able to get. There are other factors also, but even if you don't consider that, but you will not be able to see the lattice fringes clearly. The primary reason is delta E, which is coming from the thermionic source. I hope you understand. If you have any question, you can unmute yourself and ask. Any question? So delta E, as I mentioned, that it can be more than, it can be actually, it can be around 1 electron volt. And okay, for incident electron beam, and it is typically, it's suppose it passes through 50 to 100 nanometer thick foil, so your delta E can increase up to this much. This is quite serious. Even if you took a perfect source, your sample can introduce these kind of losses. It can be even larger than this, because this is not a large value, as you know that inelastic processes, these energy losses can be very, but one saving grace is that, as I mentioned in my earlier lecture, that inelastic processes happen at larger angle, right? So that is the natural protection to some extent for you, that those electrons which have undergone very large energy losses do not enter into the mm, objective lens for the imaging. They are blocked by the aperture. They are stopped by the aperture, or they just go into some other direction of the detector, some other detector, for example. Okay, I mean, they just get lost into the chamber, so they will not enter into. So finally, you worry about this energy range. So larger than this energy range, the reason is that the reason I am repeating it, that larger the energy loss for incoming electron, the electron has to go very close to the nucleus. And then only those larger energy loss processes can happen. It has to go close to the core electron. Core electrons are very close to nucleus, and then that recoil, that slingshot kind of deflection for that electron will send it to orbiting into other direction, and that's why we are saved to some extent. Otherwise, life would have been horrible. So that is the protection by laws of physics, not by any lens physics or aperture physics. Okay, please note that, or a source physics. It's basically laws of physics which prevents us. Otherwise, our chromatic would have been worse than that. Okay, just imagine that. It would be difficult to image the sample. So even if you take most perfect energy source, electron source, so your resolution is limited by spacing thickness divided by 10. So if you want to see 1 inch from resolution, you can see that your sample thickness uh, should be okay 10 okay 1 nanometer or basically less. Okay. I mean, this is only for chromatic part. Okay. There are other part, as you know, which will limit the spherical part. Um, so worse the so this is worse for thicker sample. Okay. Now this is the final point today. Before we give you the before I give you equation for resolution. Stigmatism, all of you know that, as I mentioned, that it is there in our eyes also, the lens of our eye. So this is in the other side. So far we were discussing about the confusion in the focal length along the path of electron travel. But now you see this is other dimension, right? Along the plane of lens. So this uh, confusion, contribution is because of non-symmetry. Electron beam is non-symmetric in this direction, and that happens. As I mentioned, that astigmatism can be due to the lens itself. Lens means pole pieces imperfection, because if pole pieces are not symmetric, you have seen the pole pieces already. Uh, so they are all machined on in some machine shop. So one contribution is that. Another contribution is your apertures. If apertures are non-uniform, apertures can be non-uniform when they are shipped to you. Even new ones can be machined improperly. So that can introduce stigmatism. And during the operations also, lenses undergo a lot of damages. Pole pieces are, please remember that pole pieces undergo constant bombardment of electrons. So same problem which we discussed about apertures, that apertures can get contaminated and that contamination can lead to stigmatism. Same problem can happen to the pole pieces. So please remember, all the debris from your sample, all your things which are flying from your sample, volatile chemicals, solvents, and all kinds of things, they finally land up. They can get deposited over a period of time on the pole pieces and other things. So that built up can deflect the electron beam uh, uh, out of spherical dispersion, and then and it is very obvious that you will have this stigmatism. Okay, So these are all discussed here, the reasons, all three reasons which I mentioned, that soft iron core pieces are not always machined properly. Second part, apertures, dirty apertures or imperfect apertures, then so electron beam may not be centered properly. Third thing is that even if they are machined properly, but they are not clean, so that can also lead to. Finally, so we have R for that also. We need to astigmatism can also lead to one point in the object plane forming a disk in the image plane, Gaussian image plane, and we have the radius for that disk, R AST. AST stands for astigmatism, and that is proportional again to beta. So all these three contributions are proportional to beta and proportional to delta F. Delta F, next coming lectures in HRTM, high resolution TM, we will be discussing a lot about delta F. Delta F will be is basically deciding factor again in the resolution. So resolution is decided by, you can see that defocus, this is amount of defocus. You can see resolution is decided by delta F also, not just this one. We have not discussed a lot on defocus, but we are going to discuss defocus quite a lot when we end this module by teaching phase contrast electron microscopy or high resolution electron microscopy. There, a lot of discussion will be there on delta F. A lot of research has been done on what should be the delta F. Okay, we are discussing beta value and all kinds of things, but what should be the ideal delta F? A lot of people have given, a lot of physicists have given equations. So there are various kinds of delta F. There is a Scherzer defocus is there, extended Scherzer defocus, all kinds of things are there. So then we will see that what is the information, what we call it information limit of a microscope. So can you go beyond the practical resolution limit of a microscope? How will you understand that? So there are some very interesting advanced topics. I have kept that as the last layer of the this lecture towards the end. And but these are actually, this lecture is still chota mota lecture. So okay, if you're not able to understand, you have to listen to these recordings again and again, because high resolution TM you will not be able to understand. And Barry Carter book, if you see any TM book, you will not be able to understand. Beyond this, the book becomes too complicated, because topics itself become complicated. So normally, I do not recommend reading from book beyond these topics. You may not be able to really learn anything from the book as such. So how do you fix it? That can be easily done using stigmator coils. These are additional coils, and you can do that. There is stigmator both in the illumination side and the imaging side. There are two sides of, right? One above the specimen and below the specimen. That is called illumination and the imaging chambers actually. So one example is mentioned here. You can see that there is astigmatism, there is elongation, and there is no elongation basically. There is this is corrected actually. So you can see that these are all the astigmatism is basically when your circular beam becomes elongated in one direction because of three things which I mentioned. Now we are reaching to the final point for today's lecture. We are well in time. Theoretical resolution limit. Now we all know that if there is no aberration at all in any lenses, if the lenses were perfect, then we can use Rayleigh criterion. No problem, absolutely no problem. Lambda by 2, right? You already know about that. But point always become disk. Single point source will not be imaged as a point, even if no aberration or astigmatism is present. The final size of the lens results into diffraction. So this is called diffraction limited resolution. So So that was also discussed by a scientist named Airy. Airy disk is called because of that scientist's contribution. So Airy disk is basically when the point is imaged as a disk. So central bright disk, and after that there are brighter and darker fringes. Okay, that's called Airy pattern. Okay, let me show you. This is because of multiple secondary maxima and minima. So finally you get, I think I showed you the airy disk. Let me show it again because it should have been here. What do I mean by airy disk? Yes, it is here. So if you notice, this is called the airy disk. So this is the disk which is formed here. So the point becomes not just the disk; it becomes basically a pattern, not just one single maximum, but you can see that there is a minimum, and then there is another peak, and then there is a minimum. So basically, resolution is defined by if you bring another point here, another point here, another, because this is just one point in the object plane, but there are millions and millions of these kind of points. So once you keep bringing another this kind of a feature, so when the minimum of the uh, minimum of one disk overlaps the maximum of other disks, that is called the resolution limit. That is called the diffraction resolution limit, which was given by Lord Rayleigh as well as Ernest Abbe. They reached to the similar equations. Slight difference was there. So that's why this airy disk is very important. You can see that this is a central bright spot, and then there is a dark fringe, and then there is a second one, and then there is a dark one, and then the light one. So intensity basically rapidly drops. Fine. So if somebody asks you how do you define the resolution, you can see my previous lectures. There I have explained the concept of resolution in detail, but that discussion was limited to diffraction limited resolution only. We didn't discuss much about the aberration limited or astigmatism limited or aperture limited or lens limited mm, uh, you know resolution limit, which we have discussed today, right? So, so now when we, so this is the theoretical limit, 1.22 lambda by n sine beta. N sine beta is taken as beta, n is taken as 1, and sine beta is taken as beta because these angles are very small in electron microscopy, all of you know. So you can see that Rayleigh conditions when the overall intensity profile exhibits a dip in the middle, that is above 80% of the I max, 2 points cannot be resolved. We have discussed all these points earlier, so you can go back and check. So separation of these two incoherent point sources is defined as the theoretical resolution limit of these sources. So for example, these 2 point sources, P1, P2, which they're forming disk. You can see this is the disk actually, right? This is the disk, but still they're resolved. This point has become a disk here. Okay, so this Gaussian distribution is because of intensity. This Gaussian intensity distribution is because of the central maximum from the airy disk. This is actually airy disk. From one point, there's another point. So there are all kinds of millions and millions of points. We are just comparing 2 points. So when they are too close, then these points can be considered as unresolved. Okay, but when these points are just sufficiently close that the minimum of this airy disk falls exactly at the maximum of central maximum of this neighboring disk, then they are considered as resolved, and this distance is uh, calculated as 0.61 times lambda divided by beta. If you take 2 times of this, then you can considered that as 1.22 times lambda divided by beta. Now we have all these equations. Okay, we'll put together. We'll review one by one. So our disk, because of our spherical aberration, remember that is proportional to Cs beta to the power 3. Chromatic aberration, again, you have a delta E factor here because that is very important. And then proportional to beta. Stigmatism is also proportional to beta, proportional to defocus also. Here you don't have defocus values. Here you have. So finally, that's why defocus is you have to have defocus because defocus takes care of stigmatism also. So that's why in TEM you work with finite delta F. You can understand, right? If somebody asks you why TEM has non-zero defocus while in optical microscope there is zero defocus, delta F is zero. So now you know the reason, right? So it acts like a corrector actually for okay. Now R theoretical, this is diffraction limited and stuff. Now beta is here. This if you want to decrease R theoretical, you have to increase beta. But if you increase beta, these values will go overboard, especially this because here is the cubic term. So you can balance it out and find a common minimum program like all the political parties, they do in the coalition. So so basically, some of these radii you can consider. If you see here, we have ignored for simplicity only. Just for simplicity, we have ignored this. It doesn't affect our results too much. But R theoretical square plus R square spherical and square root of that. Finally, once you so basically, once you optimize through these equations easily, then you basically beta, the collection angle optimum reaches out to 0.77 lambda to the power 1 by 4, CS to the power 1 by 4. So this is optimal collection angle which was given, but it is actually just for just to give you a feeling. Finally, we learned these processes later on. So minimum resolution, practical resolution limit. This is good number to remember after reaching all these, putting these numbers back here. You can put these numbers back here and then quick calculation for 100 kilo electron volt with CS is equal to 3 mm give beta optimum around 4.5 milliradian. So with this R minimum, this R minimum is basically the radius of the disk, which is formed by aberration, and it's basically around approximately 0.91 and CS lambda to power 3. And so basically you can see that larger the CS, and so this will be larger, and then it is energy dependent also, right, through lambda. So that is the practical resolution limit of TEM. We'll learn later on how to break this. So this is the practical resolution limit which you see in TEM brochures. In TEM brochure, this is the limit which is given. But in real sense, we'll learn later on. It's very interesting. I'll not disclose those things now. So R minimum is typically 0.25 to 2.5 to 3 angstrom, and for best high resolution instrument have got it around 1. You know all those numbers actually. It's around actually 1 angstrom. 1 angstrom typically for high resolution, but it can be very worse. It can be worse also. But you can remember that it is around 1 angstrom. Okay, without any confusion. It can be worse as 2 to 3 angstrom. 2 to 3 angstrom is a very bad number. You can't do anything with that because your D values, you won't be able to image your lattice fringes if it is so, because D values will suffer. You will not be able to see. I'll give you a way around that how can you bypass these conditions. These, please remember that these are for uh, poor people like us who cannot buy uh, microscopes with CS correction, right? So, but if you are at TIFR and or GNCSR, they have uh, this kind of a thing. So now the resolution limit has gone down to it was half an angstrom, but now it is basically it's around 35 picometer. So basically 0.3 angstrom, around 0.35 angstrom. Okay, that becomes 35 picometer, right? So you can see that from 1 angstrom to 0.3 angstrom, it requires almost 15-20 crore rupees. So if I put it in dollars, $2-3 million more just to go from 1 angstrom to okay, half of that, slightly smaller than half of that. You need to spend 2-3 times more money uh, to get that kind of a thing. Okay, so I'll end it here. I think you can read all these things. These are all I have already taught. There is nothing new. Uh, how thick is the sample? We have been discussing all the time that a high resolution at 100 keV, your sample should be less than 30 nanometer, while at 300 keV, you can afford to make it 50 nanometer before CC start controlling the resolution. Okay, so see, your chromatic aberration will start affecting. So many times you may wonder, "Arey yaar, I mean, I'm not getting good quality lattice fringes." Uh, it it may be due to your sample, because if sample is too thick, or you are working with higher atomic number elements, then you need to thin down the sample. Otherwise, you will not be able to see the chromatic aberration will be too big to get any lattice fringes resolution. D will be too much. Now you got the feeling uh, about this. This can be very, very serious. So you can review these slides. If some of you are having this problem in your day-to-day life, it is important that now you have this real life application, right? So we discussed a lot of interesting details, but now we have an application, right? Sometimes students they get puzzled. अरे यार इतना theory को पढ़ा रहे हो? Because if you do not understand those concepts, you will not understand the application. So the application is thinner the better. How much thinner? Now you have the number. How this number came? You know the reason. The resolution limit is around 1/10 of the sample thickness. Okay, so I hope that I did this big exercise to uh, give you this message. How why this thinner the better term is important, and why should you worry about uh, chromatic aberration, astigmatism, apertures, cleaning the maintaining that all kinds of you don't introduce any wet sample into the chamber. You should dry your samples so that your sample doesn't contribute to the deposition of contaminants on apertures or on the lenses. So, okay, so with that, I invite all of you to shoot your questions. Please open your mics and any questions or any comment? Amrita Lohar, I think real name is something else. Arunima, Asma, Darren, any question? Files, Madhuri, any questions? So let me know.